Hello, my name is Ethan Boger, and this is the bonus ANSYS simulation for the final project of the semester. So I've already gone through and done everything just because the assignment doesn't say from scratch, so I'm just going to walk through getting everything after the fact. But I'm going to walk through all my steps I took to get here. So for starters, because we're working with a airfoil, and ANSYS doesn't have a native way of uploading a airfoil. We have to give it points to create a line body. So we're gonna start over at airfoils tool.com, and we're working with a 2415, a NACA 2415. So we're gonna go to max camber, first digit being 2. And then the second position being 4, so that's 4 times 10, which is 40. And our thickness is 15% of the chord length. So we'll go ahead and set that. And then over here, we're just going to give ourselves as many points as possible. So we're going to start there. And then hit plot. This will give us the NACA 2415. And we'll send this to the airfoil plotter. And from here, this will let us make some small edits. So for our case, we want a meter long chord length for this NACA 2415. So we're going to change the chord length to 1000. And outside that, that's all we have to do here. I'll hit plot again. Now we actually have the plot. We're going to download this CSV file. And then you have to make some edits. Hold on, let me pull up my file real quick. Okay. So from there, you'll get something that looks like this. This title area won't be the same, but you'll name this number group, number point, number X, number Y, number Z. Since we're doing a 2D simulation, our our hashtag Z will be all 0 throughout. Then we'll take our X and Y coordinates, starting from the leading edge, going under the trailing edge, or sorry, from leading edge to trailing edge on the bottom of the airfoil, stopping at the tip, and then going back. And that's what we'll see here. That's how it should give you the off the airfoil plotter. If not, just flip it around. And then the important bit here is all these are all going to be number 1 group. And then our number point just starts at 1 and goes all the way down to 200. At the very end here, this is probably the most important part, is this 1, 1, 0. If you don't add this 1, 0, what's going to happen is in ANSYS, you'll have a small hole at the end of the airfoil because it's not connected. This is just telling ANSYS to connect your points together. That way it's one solid body. And then you just ignore all this, delete it. And then you do file, save as, and text decantered or something. Hold on. Let's see. I don't remember off the top of my head what it's called. You save as space delimited. That's it. Formatted text. Sorry. Text tab delimited. This one. I already have that in there, so don't need to worry about that. So then we're going to go over to Model Designer, and as you can see, I already have my geometry. But you start out with a surface, so you do concepts, and then you do a 3D curve. A 3D curve, you'll apply your file. Apply your file that you just generated into it. You'll get this shape right here, which is your airfoil. And then from there, we have to make our fluid domain. So I decided to go with a C-shaped fluid domain. So essentially, I started out with this C shape right here. I decided on just to be safe, that this would be, what is it exactly, actually? I don't remember off the top of my head. I believe it's 50 times the chord length. It's 50 or 15. let's see. H5. What is H5? Sorry. It is 15 meters, so 15 times the chord length. And that's the same thing for back here as well. And then we also just broke this up into 6 chunks using a face split. That just allows us to give us a little bit more flexibility with creating our mesh. From there, we did a boolean to remove the airfoil from the fluid domain to make it essentially a walled body. And these two merges here are just connecting these points up here in the bottom. For whatever reason, through face splitting, these get disconnected. So just remerging them makes the body solid again. So that's the geometry completed. From the geometry, we have to go over to our mesh, which I've got right here. So the important part is starting with our edge meshing. So the reason why we have these faces is because we want to be able to mesh different areas differently. So for this first one, what we did was this line, this line, this line, this line, this line, and this line were selected, and we're given 250 divisions with a bias factor of 50,000, and then biased in a way to where they were more condensed towards the airfoil, which is our point of interest. So we want the most meshing towards that point. So we go ahead and get that done, and then we work on our next area. So this is just this area right here. So similarly, we have our meshes being condensed towards the airfoil. That way that this area around the airfoil is our most meshed area. Then we're working on these vertical points. So these are all just hard biased, or so not biased, hard divisions. And this just kind of gives us the area over the airfoil. This front bit, same thing, just giving us some points of interest at the front so we can measure where the air is coming in from and how it's hitting the tip of the airfoil. Ideally, you would want to get as much data along this airfoil as possible. Unfortunately, using the student version of ANSYS, there are some limitations to how much you can mesh and how complicated your mesh can be. So, and you just did a face mesh over everything, just give it some quadrilaterals, just make it a little easier to work with. So this is the end result. As you can see, starting from the tip here, the mesh gets smaller and smaller and smaller and smaller until it's extremely fine towards the airfoil. And actually, from here, we can go all the way down to the edge of the airfoil. So, and then if we do a node check, I can hit hold control and select these 2 points. Down here, you'll see that actually our thickness, first layer thickness, is all the way down to 6.3 times 10 to the -3 millimeters. I've done the math for getting the proper Y plus for that first layer thickness, and it is closer to 3 times 10 to the -5 for this specific airfoil, which I was unable to attain, and it's actually probably why my results are funkier than expected. And I'll show that after this. So with our mesh, it ends up coming out to this very dense at the tip and along the airfoil and in the wake region of the airfoil as well. So with this, we can go ahead and move forward to our actual simulation. So coming in, we see my inlet coming in from the top, my outlet coming out from the back. And then we're only just go over here, go to models, make sure we're on a viscous flow. And then go to fluids, air. We were told 1.2 and 1.8 as our values. And then to start, we're going to go over to our boundary conditions, do inlet velocity. So for this, you can see how my values are not 15. So I did the math to get my Reynolds number of 1,000,000. It required a 15 meter per second velocity. So for this case, we're just going to set this to 15 to 0. This is going to mimic our 0 degree angle. Hit apply, hit close. Internal, don't really need to worry about that. Cell zone conditions, I am just want to set this to fluid. Make sure we're set to air. We are. Perfect. Okay. Internal, outlet, outlet pressure 0. Symmetry, the symmetry of these walls up here. And our wall is just the airfoil. And then keep going down here. Report definitions. This is where we're going to actually find our given CD and CL values. So the way that we did this is I just did report definition. I just click that, hit new, force report, drag or lift, and that opens up to something like this. And I just made sure to put drag coefficient instead of drag force. For these, before we run our initialization, I'm going to quickly switch this over to 1 and 0 to mimic the actual direction of the drag coefficient for a 0-degree angle. Those are set to, ow, sorry, hit my desk. Those are set to a 21-degree angle of attack from the last time when I ran this. So let's go ahead and make sure to change this one as well. So this goes to 0, and this goes to 1. And we want to change this before we run our calculations, because otherwise these values will be wrong. All right, with that set, we're going to continue going down to solution, initialize. We'll do a hybrid initialization. Quickly initialize this. This shouldn't take more than a couple seconds. Perfect, that's done. And then we'll go down to run calculations. Something we do want to make sure is correct for going forward is our reference values. So if these aren't correct, we'll get some funkiness with the converging. So just making sure viscosity is what we set to begin with, and our initial velocity is the same. That will just ensure that things work properly. So then we'll quickly run this. I have this set to 10,000 iterations. It will not take that. It will take only a couple hundred. So I'll hit calculate and let this run. So we'll see this as this runs. We're already getting close to the values we need. There it goes, just finished. All right, so we were looking for CL, CD, and CL over CD. If we get CL and CD, we can find CL over CD just by calculating that. So go here, hit compute. We get a CD value at 0 degrees of 0.202. And a CD value at 0 degrees of 0.01. And then if I pull over my document real quick, go to bonus, you can see that, whoa, I just got completely different values. Those values actually seem correct. Well, that might be that might explain some of my errors. That is awesome. Yeah, that fits a lot better with my XFLR data, given a 0.2 at 0 degrees and a 0.006. My drag coefficient is significantly higher. Not significant. I mean, yes, it's a 50% increase. But much more reasonable than the almost like 10x here. So, yeah, that is actually a lot better. I don't know what changed. I'm not going to complain though. So I'll go ahead and swap those values over after this. Actually, let me do that right now. There we go. Oh yeah, that already looks a lot more proper. All right, so continuing through, we were asked to do some contours. So go down to contours, contour. Um, our first contour is our velocity contour, um, which if we come in here, we see our stagnation point forms right at the tip, which is what we're expecting. And we're seeing our peaks, especially along the top of the airfoil, and then it coming off the bottom and this not really disconnecting, which is what we like to see. So we're going to quickly save this. And just take a little screenshot of this. Just like that. Go ahead and save this. So let me run velocity 0. Save. Yes, replace. So these actually seem correct, and I don't know what happened with my first simulation. But we're going to go with these new values. And then this is our static pressure, which is, we're expecting a very stable pressure coming in. And as it meets the wall, these are actually interfering. We're seeing a massive pressure jump as it hits the wall with a low pressure region up top and a higher pressure region in the bottom, creating our lift, which is what we want. And very little pressure in this main region, which is what we're expecting. So I will also just go over our 10-degree angle of attack, because that's the other point we were interested in finding. Interesting in finding the contours for. Sorry, got a little distracted there. So I did some math on the side. So instead of re-angling our airfoil, we're just going to change what direction the velocity is coming from. So to get a 10 equivalent of a 10-degree angle of attack, we're going to change our velocity to an x component of 14.7721 with a y component of 2.6047. Just like that. And we'll hit apply and close. So now our velocity is coming up from a 10-degree angle. 10-degree angle. And then the important thing before we continue is we have to change our CD values. Because if we're taking CD as if the velocity was coming along the body, we'll get very wrong values. So I'll change this over to, for drag, 0.9848. And for our Y, we get 0.1736. And this was just found using our angle of attack. Angle of attack multiplying cosine of that and sine of that, and vice versa for lift and lift and drag. Since our drag goes with the direction of flow and our lift goes perpendicular to that. So we get very similar values, but often the reciprocal of them. Not the reciprocal, the opposite of them. So like for this case, x and y are flipped, and x is actually negative in this case. And this one is 0.94. Sorry, 9848 again. Just like that. Okay. And then we'll come back here and do initialization again. Initialize. Let this run. We've initialized. We'll do run calculation again, and we'll calculate this. Once again, it shouldn't take too long. Just let it run real quick. And we're already getting close to that. There it goes. All right. So we'll ignore that for the time being. So we'll go over to CD again, and we'll compute. This time we're getting 0.67, which if I compare to our master doc right here for this, in my original run, I got the same value. And for a similar CD in XFLR 5, they got 0.012, which is 6 times less. For whatever reason, my CD value does seem to be significantly larger than expected when comparing to XLR 5. I've tried several things. I'm assuming it's my meshing, but I'm unable to confirm that. And we'll compute this as well. We get 0.67, which is the same value I got on my first run. So that is what we were expecting. And we'll go back to contours. Static pressure, display. So the important part that we're seeing here is that this air is actually hitting down here, which is what we're expecting. And low pressure region on top, higher pressure region on the bottom. It's what we want to see. And then we'll go ahead and go to velocity, compare velocity. So with the velocity, what we're seeing is our stagnation point has gone lower onto the past the leading edge onto the lower body, which is what we were expecting because the air is coming up here, it's hitting here, and flow is going both directions, so we get a stagnation point. We're seeing a higher speed up top, which means we're going to generate a lower pressure, and a lower speed on the bottom, which means we're going to generate higher pressure. The important bit about this, our wake angle, is coming up and off here. We're also seeing a growing boundary layer here as this air begins to detach off the surface of the airfoil. And as I grow my angle of attack, that's when I get further and further up. So like it's very noticeable at 21 degrees. It's actually like almost up to here as we approach stall. And just comparing results to XLR 5, we see a much more stable curve here for our CL. Like we're actually seeing this as it hits its stall point and coming down. Versus for ANSYS, what we're actually seeing here is a more linear relationship, which is what we'd expect closer to an INVISTA potential flow. I'd have to calculate the exact value of this, but we're very close to 0.11. Sorry, not close to 0.11. We're very just not close to 0.11, but we have a very linear relationship, which is not what we expect from this, which means there's definitely something wrong with the simulation, whether that's a meshing issue or whatnot. Over here, our CD, we're seeing a very similar type of relationship on this exponential growth. But for ANSYS, we're getting a lot more off of that very quickly. And then we see that over here for XFL, comparing our XFL 5.5 and our ANSYS, we do see this increase initially and this dying out. It's less drastic than this because we're seeing a very similar, almost linear relationship here, which is giving this almost horizontal line. It's almost as if our CL is growing at a similar pace as our CD, where it really shouldn't be that case, where it really should be we're seeing this jump in CL and this like as CL jumps, CD is jumping with it, but at a much higher rate. And this is because as you generate more lift, you're getting a negative effect of additional drag, of that pressure drag that's coming from that increased surface area. But we'll just go ahead and change this out with our new values because that actually gave us the correct values. Static pressure 0. So, yeah, it looks more reasonable. And we'll change this out as well. And we'll make this our velocity 0. There we go. So that's more reasonable. Earlier, this was like we got spike here and spike there. So I did something with our wrong when I initially saw 0 degree. But this is what our final results look like. So thank you.